In this lesson, we introduced the topic of electromagnetic induction by talking about magnetic flux, and here are the objectives. Now, given the observation that a current-carrying wire generates a magnetic field around it, in the 1800s, Michael Faraday and Joseph Henry were both independently investigating whether the opposite also holds true. In other words, they were asking, if a current produces a magnetic field, can a magnetic field also produce a current? And what they found is that the answer is yes, but only if the magnetic field is changing relative to the wire. To understand that a bit more, let's look at a few examples. Here I have a bar magnet with a north and a south pole and a loop of wire, and the bar magnet generates a magnetic field around it, which I can illustrate with field lines, and I'm going to draw the field lines that emanate from the north pole of the magnet. Recall that magnetic field lines point in the direction that the north pole of a compass would point, so they point outwards from the north pole of a magnet, and also that they're closer together, like they are here, where the field is stronger, than they are out here, where the field is weaker, further away from the magnet. Now, if I have a setup like this, with a bar magnet and a loop of wire, I don't see any current moving through the wire if I just have them stationary relative to each other. So there's no movement of the two relative to each other. However, if I have the same bar magnet and the same loop of wire, and now, instead of letting them sit stationary next to each other, I move the bar magnet upwards towards the loop of wire, then I will actually see a current induced in the wire, and the current's going to go in this direction. It's going to go clockwise in this case. Importantly, this current only flows while the bar magnet is moving relative to the wire. Once I bring it to rest, let's say up here, even though it's closer, now there's no current anymore. So it's not the position of the two relative to each other, it's actually their movement relative to each other. If I do the opposite, I start from my bar magnet and coil or loop setup that I had before, and now I move the bar magnet in the opposite direction, I get a current induced in the wire that's going in the opposite direction. And once again, it's only flowing, the current is only flowing when the two are moving relative to each other. When I stop the bar magnet, let's say down here, then I see no more current. So what do these two cases have in common? They have in common that the magnetic field enclosed in the loop of wire is changing. When the magnetic field inside the wire is changing, because I'm moving the bar magnet closer to it or away from it, then I get a current flowing in the wire. But when that magnetic field is not changing, as in this case over here, or after I stop moving the bar magnet in either of these cases, then again I don't see a current flowing. So now we're going to talk about some language to make that description a bit more precise. And the first term that we'll introduce is the concept of magnetic flux. Magnetic flux has the symbol phi or phi, and we'll put a B here to indicate that it's magnetic. Now, let's take a look at this picture over here. Magnetic flux is an indication of how many field lines are passing through a loop. So if we take a look at this loop, let's say this loop has area A, and it's sitting in a magnetic field of field strength B. In this orientation, all of the lines are passing through the loop. But I could take the same area loop, shown here, and the same magnetic field strength, B, and tilt the loop, and now fewer lines are passing through it, just because of the orientation. So if magnetic flux is a measure of how much of a magnetic field is passing through a loop, or in other words, how many field lines are passing through a loop, we need to take these three things into account: the field strength, the area of the loop, and then the orientation of the two relative to each other. So we define the magnetic flux as being the product of the magnetic field strength B, the area of the loop A, and the cosine of the angle in between them. And here we need to be careful about how we define that angle. We're going to take the normal to the loop of the wire, so a line that is 90 degrees to the plane of the loop of wire, and find the angle between that and the magnetic field, which I'm drawing again here with the arrow. So this angle here is theta. Theta is the angle between the normal to the plane of the loop and the magnetic field. In this example that we started off with, the normal to the loop is here, and so it's pointing in the same direction as the magnetic field. Theta is 0 degrees. The area A is measured in meters squared, and the units of magnetic flux are a new unit that we haven't encountered before called the Weber, also pronounced the Weber, and with this symbol. So magnetic flux is in units of Webers, and area is in units of meters squared. Cosine theta doesn't have any units, so by rearranging, you can see that a possible unit for the magnetic field strength would be the Weber per meter squared. And 1 Weber per meter squared is equivalent to 1 Tesla. So Tesla is a unit of magnetic field strength, so is Weber per meter squared. Let's introduce a little bit more language. We've just defined the magnetic flux through a loop phi sub b, and earlier I said that you can think of the flux as representing the number of magnetic field lines that are passing through the loop. So if we take a look at these two examples, we've got the same magnetic field strength in both cases. B is staying the same, and the area of the loop is staying the same. But because the orientation of the loop is changing, I'm changing the number of field lines that cut the loop here. Here I only have 2 if we ignore the ones at the edge, and here I have 4. So the flux is changing. Now you might be saying, well wait, that doesn't really make sense. The number of field lines you have in a diagram is essentially arbitrary as long as it's internally consistent, so how can that mean anything? And that's right, but really what we're concerned with here is changes in flux. So we don't so much care about the absolute number of field lines that are passing through or cutting a loop. We care about how that's changing. So this definition works. So the flux can be thought of as the number of field lines passing through the loop, and here that's changing from, let's call this example 1 to example 2. What's not changing here is the flux density. The flux density is represented by the density of the field lines, and as we've talked about before, that represents the magnetic field strength and is given the symbol B. So flux density is just another name for magnetic field strength, or B. So there are some different terms to get used to here, but again, flux density just means the same thing as magnetic field strength. And the word density might make some intuitive sense, because if I were to increase the magnetic field strength, then I would have to show that in the diagram by increasing the density, the closeness together of the field lines. Now that we have this kind of language, we can think back to the examples we gave earlier in the lesson. When we moved a bar magnet closer to or further away from a loop of wire, while it was moving, we saw a current induced in the wire. So now we can talk about that in terms of magnetic flux. What we were doing was changing the magnetic flux that was passing through the loop of wire. So here's an illustration of a loop of wire sitting in an external magnetic field that's pointing into the page. So perhaps this is being created by a bar magnet that we're holding in our hand that has a north pole pointing towards the screen. If we hold it stationary, this magnetic field doesn't change. But if we start moving that bar magnet and its north pole towards the screen, then this magnetic field strength will start increasing. And most importantly, what we're interested in is the magnetic field inside the loop. So the flux is going to go up because the magnetic field B is increasing inside the loop. If we think of our equation, phi sub B is equal to BA cos theta, what we're doing here is we're increasing the magnetic field strength, and that is going to induce a current in the wire. Now there are other ways to induce a current in the wire as well, and in fact increasing the magnetic field strength in that way is usually not very practical. More typically what we're going to do is change the area, or especially change the angle. So we could change the area by making the loop bigger or by making the loop smaller, and you can see that a bigger or smaller loop encloses a different number of field lines. It changes the magnetic flux through the loop. We could also keep the area of the loop the same size, but move the loop out of the field. So if you imagine the field has an edge here, then if the loop is over here, only the part of the loop that is inside the field is enclosing any magnetic field lines, and so moving it out of the field is going to change the flux as well. So those are ways that we could change the effective area that is in the field. We could also change the angle, that is, change the angle between the normal to the loop and the magnetic field. In other words, we could rotate the loop. And this is what the generators that provide power to your house are doing. They're rotating loops in magnetic fields. So if you imagine rotating this 90 degrees, we'd be looking at it end on like this, and now there would be no field lines at all passing through the loop. And if we were in an intermediate orientation, we'd have an intermediate magnetic flux through the loop. So spinning this loop of wire in an external magnetic field would be a way of continually changing the magnetic flux that's passing through the loop. And again, this is how the generators that provide AC power to our houses work. This lesson's been an introduction to the concept of electromagnetic induction, focused on the idea of magnetic flux through a loop of wire, and we've seen some examples of how changing that magnetic flux induces a current. Over the next couple of lessons, we'll look at this more quantitatively to understand how big of an EMF is generated and in what direction the current flows.